friends, welcome to CEC Live Lectures. I am Dr. Pavitra Bharadwaj. I am Associate Professor at Jesus and Mary College, University of Delhi in the Department of Computer Science. So friends, we have been discussing the topic of operating system in the last 4 or 5 lectures, and today we'll be continuing with that. So if you recall, we were talking about process management and process scheduling in the previous series. So we are going to talk about the same topic. We are going to take it forward, that how processes are managed by the operating system, and basically in today's lecture we will be talking about process scheduling. That is, how does the operating system schedule processes or assign processes to the CPU so that a perfect balance is created between the processes which are executing in the CPU and between the processes which are going for the input output. So as we all know, the basic function of the operating system is to enhance the efficiency of the computer system, to enhance the throughput of the computer system. So in this regard, process management is a key function. So we understand that process scheduling, basically it is the aim of process scheduling is to maximize the CPU use, like in case of multi-programming system. So it is always the responsibility of the operating system to keep assigning a process to the CPU, one or the other process to the CPU, so that the idle time for the CPU is minimized. And in time sharing system, process scheduling is very important because it will allow for processes to switch quickly between the on the CPU, so that the user is not able to realize, or the user is not able to perceive that how the switch is taking place between one process and the other. So what does the process scheduler do? A process scheduler basically will select amongst all the available processes for next execution on the CPU. So out of there is a queue. We are going to talk about the concept of queue, and out of the available processes, which is the next process which is going to go for the execution in the CPU. So process scheduling is basically it is a task of maintaining queues of processes. So when we say queues of processes, we mean 3 types of queues exist in any operating system. The first type of queue is the job queue. So job queue is basically the set of all the processes which are available in the system. Then next type of queue is a ready queue. Now in a ready queue, it contains a set of those processes which are residing in the main memory. That is, these are ready processes only waiting for execution by the CPU. So the CPU will pick up the process which is there in the ready queue. And then the next queue is the device queue. That is a set of processes which are waiting for an input output device. Say for example, if there is a process which is executing in the CPU, and then it needs to read some data from the disk. So then the process will have to enter the device queue of the disk. So every device will have its own queue, and every process which needs to access that device has to enter the device queue for that respective device. And processes they keep migrating from one queue to the other. That is, they go from the job queue to the ready queue to the device queue and back to the ready queue. So they keep on moving. Now when you talk about the ready queue, basically, so a ready queue is it is in the form of a linked list. The data structure, if we understand, it's in the form of a linked list, where every node or every process control block is actually has 2 pointers. That is, the initial the first process control block or the queue header will actually have a pointer to the next process control block and to the tail or to the last process control block in that particular queue. And every process control block also has a pointer to the next process control block. So therefore we can say that these process control blocks in a ready queue, they are linked to each other. They are they are having a reference point to each other. The processor which is the process which is last in the queue, the process which is first in the queue, and the process which is next to the process being executed. So now process scheduling is, most commonly process scheduling is explained using a queuing diagram. So in this queuing diagram, if you see, we can see that we have queues, we have resources, and we have flows. So if you see here, the rectangles which are shown, these are the queues, like the ready queue and the input output queue, and the circles are basically the resources for which queues are being formed, like the CPU or the IO. And the arrows here, they show the flow of process, how it is moving on. So when a process is actually executing in the CPU, so it is actually, it comes from the ready queue. So from the ready queue, a process may be assigned to the CPU. Now when a process is assigned to a CPU, it can have multiple fates. So the first is that the process, simply the CPU completes the execution and the process is terminated, it is ended. That is one scenario. The other scenario could be that the process, while it is executing in the CPU, there is an IO request which arises, and the process now goes for an input output queue. So when it requires an input output, say for example it requires some input from the user, or it requires some data to be read from the disk, whatsoever, so then the process has to enter the IO queue of the respective device. Another scenario could be that while the CPU is executing a process, the time slice, in case of time sharing systems, the time slice has expired. So the CPU's control is taken from the process, and the process is put back into the ready queue. So then it will wait for the next term. Another scenario could be that the process, it breaks or it forks into a child process. So when it breaks into a child process, then most operating systems will ask the process to wait until the child completes execution. So when the child process completes execution, only then the process execution of the parent process will resume. And another scenario could be that there is another type of interrupt, a system call which is generated. So then the process has to wait for that interrupt, and then it goes back. So therefore all these scenarios, they can be very easily explained by way of a queuing diagram, which represents how process scheduling takes place, or how processes are assigned to the CPU. So scheduler, basically, these are scenarios, or these are programs, we can say. These are modules which are going to work towards how this process, entire mechanism is going to work. Because we know that a process will migrate from among the scheduling queues throughout its lifetime, right? So the operating system has to select, for scheduling purpose, the processes from the queues, whether it is a ready queue or it is an IO queue. It has to select the process in some manner, right? So this selection is carried out by an appropriate scheduler. Which process exactly goes to the CPU has to be decided by the appropriate scheduler. So schedulers, they can be two types of schedulers. In fact, we say that there are three types of schedulers that we talk about, but primarily we say there are two types of schedulers. That is, first type of scheduler is the short-term scheduler, which we also known as the CPU scheduler. And the second type of scheduler is a long-term scheduler, or we call as the job scheduler. So if we understand this, that the job of the short-term scheduler is to pick up the process, to select the process which is to be executed by the CPU, which is next to be allocated to the CPU, right? So short-term scheduler is invoked very frequently, because it must run very fast, because the CPU will complete the task, and as soon as a task completes, which is few milliseconds, then the new process is to be assigned to the CPU. So therefore a CPU scheduler or a short-term scheduler has to function all the time. And in a few operating systems, the only scheduler which is there is the CPU scheduler only, because it picks up the job and it assigns it to the CPU. Whereas another type of scheduler, which is known as a job or long-term scheduler, it selects the processes which should be brought into the ready queue. So long-term schedulers, they are invoked very infrequently, sometimes in seconds, sometimes even in minutes, because they are really slow. Because long-term schedulers, it will bring the process here. It will bring the process into the ready queue, and from that the short term scheduler is going to pick it up. So the long term scheduler controls the degree of multi-programming which is occurring in the system. Why? Because in whatever processes are present in the ready queue, those processes are ultimately going to be executed. So out of those processes, the long term scheduler is going to pick up and assign the process to the CPU. So processes, they can be described as either input output bound processes, or they can be described as CPU bound processes. Now what is input output bound process? So that is a process which spends more time doing input output than computations. So it has got many short CPU bursts, but most of the time it is busy in the input output processes. Then there is another type like CPU bound process, which is doing computations for most amount of time, and very few or very long CPU bursts are going to take place, because most of the time the process is acquiring the CPU. So now there can be disadvantages to both the processes, both types of processes, if they are not provided in a balanced manner. For example, if we have more input output bound processes, then the CPU is going to remain idle for most amount of time, because all the time the processes are in the input output mode, and the input output queues will also be longer. If it is a CPU bound process, then the input output devices will remain idle and the CPU will constantly be working. So that can also affect the efficiency. So therefore it is very important that the scheduler will try to create a good process mix, so that there is equal amount of input output and CPU bound processes, so that there is a balance which is created and both types of resources are used at the optimum levels. Now there is another type of scheduler which is introduced or which is talked about, that is known as the medium level or medium term scheduling. Now medium term scheduling is basically used in case of time sharing systems, where we have a concept called swapping basically. So this will also this is adding this can be added, the medium term schedulers can be added if we need to decrease the degree of multi-programming, or if we need to decrease the number of processes which are residing in the ready queue. So what is done in case of medium term scheduling? So medium term scheduler will remove the process from the memory and it will store it on the disk, and then it will bring the process back from the disk to continue execution. So therefore on and off this movement of processes from the memory to the disk and back to the memory is going to take place by the medium term scheduler. So when the process is brought into the ready queue, it is called swapping in. When the process is brought out from the CPU and put back into the disk, it is known as swapping out. So continuously the processes are moving in and out of the ready queue. So the process is swapped out and is later swapped in by medium term scheduler. Swapping may be necessary because it is to improve the process mix, or because a change in memory requirements has overcommitted available memory. So therefore it requires that memory has to be freed up. So certain processes need to be moved out of the memory in this case. Then if we talk about how multitasking happens in mobile systems, so in mobile systems, like we have the earlier versions of the iOS mobile, they allowed only one process to run, and other processes whichever were there had to be suspended. But now later on, with the real estate, screen real time and user interface limits of iOS, it is found that single foreground processes are available which are controlled via the user interface, and there can be multiple processes which are running in the background in memory. So so not only the display and with also the limits, so therefore now multitasking in case of mobile systems are becoming more and more possible and more rigorous, because this it is basically the Android runs foreground and background both with fewer limits. So background processes, they will use services to perform tasks, and services they can keep running even if background processes are suspended. So because there are services which do not have any user interface and they require very small amount of memory. So therefore in case of mobile operating system also we see that there is a considerable amount of multitasking which has been built in, right. So therefore now after we discuss about scheduling and we understand this concept of how processes move in and move out of the CPU, now it is very important to note that a large number of times a process may be moving out of the CPU because of the scenarios that we've already explained, that the process is not complete and yet it is going to be going out of the CPU, it has to leave the CPU, right. So in this case it is a context switch which is happening by the CPU, because the CPU now has to move on to another process, leaving one process in between, right. So therefore a very specific or a very specialized mechanism is to be adopted which is known as the context switch. So interrupts can cause the operating system to change a CPU from the current task to run a kernel routine, right. So this happens very frequently and in on general purpose system. So whenever an interrupt will occur, the system will save the current context of the process running on the CPU, and it can, so that it can later restore that context when its processing is done. So essentially it suspends the process and then it resumes it when the kernel call is over. So the context is represented in the process control block of the process, and what all is included. So it includes the value of the CPU registers, the process state, and the memory management information. So generically we perform a state save of the current state of the CPU, whether it is a kernel or a user mode, and then a state restore to resume operations. So therefore this keeps on happening, whether the CPU is working or whether the kernel is the OS is working in a kernel mode or it is working in the CPU in the user mode. Continuously this back and forth restore and resuming is happening. So when the CPU will switch to another process, the system will save the state of the old process and it will load the saved state for the new process via a context switch. So context switch is that mechanism by way of which the CPU is going to store the state, the various attributes like the registers, the process, the memory, etc., and it will save it, and then it will move on to a new process, and from that, after the new process is completed, it will go back to the previous context. So this context back and forth will keep happening. So context of a process is generally saved or it is represented in the process control block of the given process. Now definitely this is a overhead, right, because the system is not doing any useful work while it is switching. So the more complex the operating system and the process control block, the longer time it is going to take the process the context switch. Say for example, if the context switch, it takes 10 milliseconds for one process to go from to the CPU to the other process, and the process actually requires say 100 milliseconds. So in that case it is almost 9% of the CPU time which is being wasted only in the context switching and not doing any real hardcore processing or execution. So this time of context switch is also dependent upon hardware support. So some hardwares they provide multiple sets of registers per CPU. So multiple sets of registers means that they can store multiple context at any given time, right. So therefore this context switch mechanism has to be looked at in perspective with different types of operating system. Different operating system like Unix or Windows or Solaris, they have their own mechanisms of providing this context switch and of reducing the overheads which are involved or which are as a part of this kind of context switch mechanism. Next we talk about the different types of operations which are possible on processes. Now processes in most systems they execute concurrently, that is at the same time multiple processes are executing, and they are created and they are deleted dynamically. So system must provide mechanisms for creation of processes, for termination processes, and for different types of operations that may be happening to the processes. Now process creation basically is a mechanism or is a means by which new processes can be created. So parent processes, they will create child processes, which in turn will create another processes. So it's actually a tree of processes which is created, and generally the processes are identified and managed via a unique process ID. So we will be referring to process ID as PID for our discussion sake. So every process can create or produce n number of other processes, and each other process or each child process will further process, and for the system to identify, there is a process ID which will be used for all internal references to the process. Now for process creation, when process creation takes place, that is when one process it produces child processes. So there are several possibilities in the way how resources are going to be shared between those processes which are created. So first possibility is that the parent and the child, they will share all the resources. That is, whatever resources are allocated by the system, say the memory or the registers, or the other resources, whatever resources are owned by the parent, they will be shared by the child resources. The another possibility of resource sharing could be that children will share a subset of parents' resources. So whatever resources a parent has been allocated, child can only take a subset of those resources. And the third is that parent and child share no resources at all. That is, the child process will claim for its own resources. Now the first two mechanisms, where the parent shares the resources or parent gives a subset of the resources, these are ways by which resource allocation is controlled by various operating systems. Otherwise, as new processes are created by each parent, there will be a scarcity of resources which can be given to the future processes which are arising. By this way, by controlling the way resources are distributed, each parent can generate n number of children, but the resources which are allocated to the process will remain constant. So therefore this is a way of managing resources efficiently by certain operating system. Then there can be execution options also, that is, both parent and child process, they will execute concurrently. In some operating systems, it says that parent will wait, it will stop its execution until the child process completes or terminates its execution. So processes can work in different fashions, but when the process it executes its last statement, okay, then it asks the operating system to delete it using the exit system call. So once the process is complete, then it will give us exit system call, and then the process goes in for deletion. So when it says the exit system call is given, so it will return the status data from all the child processes to the parent. So the parent process is actually going to go in a wait state. So wait state means that the parent wants to execute, but it is waiting for all the child processes to execute. Now process resources, including physical and virtual memory, all the open files and the input output buffers, are deallocated by the operating system when the process goes for termination. So termination can occur in other circumstances only. It is not just that successful completion is going to termination. There can be other scenarios also which will lead to process termination. So we will be continuing with process termination in the next lecture. Till then, keep watching CEC. Thank you.